Good morning, students. Today we are going to discuss about fundamentals of magnetic circuit in electrical machines 1. You know, the silent hero or root of all electrical machine for their working is based on magnetic fields. The silent hero is nothing but magnetic fields. The magnetic fields can be created either by permanent magnet or electromagnet. These magnetic effects play important role in design of many electrical or electronic systems used today. And here in electrical machines, the more concept of function of working of motors, generators, transformers are all based on this magnetic field effect. And some of the other applications are loudspeakers, relays, some medical equipments. So the magnetic field effect plays vital role in many equipments. And magnet, we know what is magnet, correct? The substance that attract the iron pieces of some other metal is called magnet. A magnet generally classified into a permanent magnet and temporary magnet, or the other name for temporary magnet is called electromagnet, correct? The permanent magnet materials are cobalt, steel, or tungsten, correct. These permanent application of the permanent magnet is very few because of some limitations in permanent magnet. Okay, so in first semester and second semester you would have seen in labs ammeter, voltmeter, correct, moving coil ammeter, moving coil voltmeter. There they use a permanent magnet. Okay, so and electromagnet, um, the limitations in permanent magnet is overcome by the temporary magnet or electromagnet. Mm, and very interesting thing is in permanent magnet, no, we'll have see here we have N and S. These poles are fixed. We cannot change here as N pole, here as S pole. But in electromagnet, we can change by changing the direction of current. We can change the N and S polarity. Okay. And how the electromagnet is created or produced is nothing but by making coils over a soft iron piece or silicon steel. We can um, make use of these by allowing current flow through the coil. It, it acts as an electromagnet. Okay. Then magnetic lines of force or nothing but some imaginary lines only. Correct. So the imaginary magnetic lines which travel from north pole to south pole. See here in this diagram. Even if you make a magnet under a paper, no, if you spread uh, iron particles over it, it forms path like this. Okay, we can see that. mm, so magnetic lines of force are nothing but imaginary lines which travel from north pole to south pole outside the magnet, and the south pole to north pole inside the magnet, correct. And the magnetic field, the region around the magnetic lines of force act, is called as magnetic field. And we can understand the presence of magnetic field by attraction or repulsion force, correct. So you know, if two magnets of same poles repel each other and opposite poles attract each other, correct, then it will have some properties of magnetic lines of force here. So we know magnetic lines of force travels from north pole to south pole, and then see here, see here, from north pole to south pole they travel, and they don't crash each other. And then they move, they are the three-dimensional one, extending to infinity, theoretically saying, correct. And see, magnetic lines of force are continuous, and these lines of force enter or leave a magnet surface at right angles, and they cannot cross each other. And in the same direction, magnetic lines of force in the same direction tend to repel each other. See here, that's why they have the space between them, correct. They are not mm, concentrated at one point, correct. Magnetic lines of force occupy three-dimensional space, extending to infinity. Ampere's right hand rule, and this, if you grasp a conductor with our right hand, no, the thumb finger shows the direction of current. Here in a straight conductor, the magnetic flux will be in circular fashion, correct? It will not start or it will not end anywhere. Okay. So there is no poles also. There is no such a north pole or south pole for a conductor carrying current. That is a straight conductor carrying current. But the same thing, if you take it as a solenoid, you know what is solenoid? Coil wound on a soft iron piece, correct? And this is a current entering point, and if you grasp your right hand here, no, if you keep your right hand here, no, the thumb finger shows the direction of flux as well as the north pole, correct? Here the direction of the other four fingers shows the direction of current. Okay, so if you um, want to change the north pole and south pole, generally for this one, இங்க வந்து north pole இருக்கு, இங்க south pole இருக்கு வச்சுக்கோங்க. Suppose if I want to make a north pole here, means I have to apply current here, correct? That is, the entering point of current should be here, so that the direction, see here, the direction of current is just opposite. Clear? So now, no, this becomes N pole and this becomes S pole. Okay. See here, this is a solenoid where the N pole and S pole are um, created. Correct. Then some of the parameters used in electromagnets, you will see here. Magnetic flux, the total number of lines of force in the magnetic field is called as magnetic flux. It is denoted by phi. Right. Magnetic flux density. Density, generally, you know, any density divided by area, correct? So flux density means flux per area. Similarly, magnetomotive force, which is similar to electromotive force. Here, the driving force required to drive the magnetic flux through a magnetic circuit. This is a product of N and I. N is number of number of turns, and I is the current flowing through the conductor. Correct? Or turns, current flowing through the turns. Clear? So MMF can be increased either by increasing the number of turns or increasing the amount of current. Okay, so MMF is equal to Ni. Then the reluctance is similar to the resistance, which opposes the magnetic flux. Permeance is reciprocal of reluctance. And magnetic field strength, it is a force experienced by the unit north pole placed at the point. It is denoted by H. So flux or force per flux is called as a magnetic field strength. It is also given by H is equal to B by mu. Permeability, this is a word coming from the root permeate. Permeate means penetrate or pass through and often become widespread throughout something. What is here widespreading throughout? Magnetic flux or magnetic lines of force, correct? Hence, here we use the word permeability, which is nothing but the another name for permeability is magnetic conductivity of the ion. Okay, it is given by mu. Mu is equal to B by H. Mu is equal to mu naught mu R. Mu naught is 4 pi into 10 for minus 7 Henry per meter. Mu R is relative permeability. The relative permeability of the medium will change, but its value is 1 for air as well as free space or vacuum. And in this case, it's very interesting to understand the difference between the permittivity and permeability. Permittivity measures the ability of a material to store energy within the material. This word comes to, or this word is responsible for electrostatic field. Permeability is responsible for electromagnetic field. It's a measure of ability of a material to support the formation of magnetic field. Okay, so permittivity for electrostatic field, permeability is for electromagnetic field. Clear? And there is a comparison between electric and magnetic circuit that we'll discuss in next video. Thank you all for watching this.